And the second problem for today is called as mapping. Again, there are two types of sensors, LiDAR and camera. So let's do it quickly for both of them. First, the LiDAR, which is the one that I like. So that's my robot. And that's suppose at a known position Q. And that's where it's looking at. And this is the actual map, which is unknown. I need to find out what this map is. Say map. So the laser beam strikes at d alpha at a distance of alpha. So I know that there's an obstacle O in my local coordinate frame Q, which is at a distance of d alpha, cos alpha, and sine alpha. So what I'll do is I need the same O at the world coordinate frame. I know my position, let's assume that. So using a transformation, I can just transform it into the world. And because I can transform it into the world, I can just take an empty canvas and just project whatever point comes over here directly onto this thing. So that's the actual LiDAR image. Let the robot, that's when the robot took the image from here. So now let's have an obstacle here as well. And let the robot travel around over here and take this image. So it'll actually take this image and it'll be able to see all these things up. So I keep on putting all the dots into the image. There is one caveat though. Sometimes you believe that there's an obstacle at this position. Sometimes you believe that there's no obstacle at this position. So the same point will report it multiple times. Sometimes there's obstacle, sometimes there's non-obstacle. What you do is take a majority vote or a probabilistic fusion. When the robot is near the obstacle, it will be able to look at it more clearly. That's when we are using the entire map. If you just need the corners like previously to save memory, you can only project the corners onto this map. And similarly for the case of the camera. So that's my camera. So it looks at some objects. And this time let me say that there's a stereo camera. So there's a door, there's a window. Using any image processing library, I can get all the corners. So I can get U and V of the landmark in the image coordinate frame. Because I have a stereo, I can get the landmark at the robot's coordinate frame, and suppose I know my position, I can get the landmark in the world coordinate frame by a transformation, which is the pose of the robot. So that's what is mapping. So you log everything up. Now here also there's a caveat that for exactly the same object, for exactly the same corner, sometimes it will be reported as 3.4, sometimes it will be reported as 3.5, sometimes it will be reported as 2.9, 5.4. Take the average or do an optimization or do whatever to find out what the true coordinates are, and that's exactly what we do. Now there's something which is interesting around over here, and let's write down both the problem, localization and mapping. So in localization, what did I do? I took a LiDAR image, I took a map, and then I looked at which transformation of the LiDAR image best matches, or I looked at a corner that I observed in my frame of reference. I look at the same corner, where is it in the world, and then I try to find out the transformation such that the corner in my coordinate frame transformed to the world as per the assumed position is as close as possible where it is the world is. So the input is a map which is nothing but all landmarks position and the output is position, which previously we denoted like this, but as of now you just need the position. Now let's come to mapping. What did I do? I looked at the landmark. I knew exactly where I was looking at that landmark. So the window corner, the door corner, in case of an image, or in case of a LiDAR image, the actual corner, or sometimes the entire LiDAR image. I know exactly what am I looking at in my coordinate frame of reference. Stereo, I could do the depth calculation and transform it with my coordinate frame of reference. In LiDAR, of course, it gives you d alpha, cos alpha, sin alpha, the position. I transformed this in the world coordinate frame, assuming my known position, and then I kept on projecting it onto a map. I kept on projecting it onto a picture. So my input was a position and my output was a map or all landmarks position. And the output of one algorithm is the input of the other, and the input of one algorithm is output for the other. So in reality, I neither know position nor map. So I cannot solve this problem. I neither know the position, I not know the map. So because I don't know the position, I cannot do mapping. And because I don't know the map, I cannot do localization. And that's exactly the problem that we face when we actually unpack a new robot. After all the pictures are taken, it's okay, but now somebody has to start programming it. And that somebody, which is a student, says that I need two things always. Without that, all your AI theory I'll not be able to apply. The first is my own position, and the second is how does the world look like, which is the map. And me as in charge of the robotics laboratory will say, I neither have the map, nor do I have a position. It's your job, you're the programmer, you find that out. The technique that we use, of course, it's called as simultaneous localization and mapping. So I cannot do mapping because I don't have location. I cannot do localization because I don't have a map. So I say, let's simultaneously solve this thing up. I'll only take it intuitively again. So this is a map only for you and me to see. It doesn't, robot doesn't know about it. And the robot always starts a journey from the charger. So robot always starts its journey from the charger. So position at time 0 is origin, which is basically written at the transformation from world to position at time 0 is identity. Oops, identity. I'm not going to the mathematics anyhow. So good. Now what do I do is I observe what these corners are. So I observe what these corners are. How many corners can I see? I can look at this corner, I can look at this corner, and I can probably look at this corner. This one's, I mean, I have a limited field of view which is here, so I can look at 3 corners. So I know these corners in my own frame of reference, and because I know them in my own frame of reference, therefore I also know that I'm at origin. So my frame of reference and world frame of reference are currently exactly the same thing. So that's how I make a map. So let's say this is my map, and my map currently has 3 corners like this. This part of the map is known. Alternatively, if you were using a LiDAR sensor, you can also actually map the entire LiDAR image that you see. All these things I can only look at in this region. So, and some parts of this thing. That's what I can look at. So that's my LiDAR image. Let's go to the corner cases. So there are 3 corners, and that's sometimes how I denote it. So this is my position at time 0. And I can look at corner 1, corner 2, corner 3. So I know my position, which is identity. I know these corners with respect to myself. So I know the transformation between this corner and myself, this corner and myself, this corner and myself. So I know this is this transformation times this transformations, which is the same as these transformation as of now. So I can calculate these 3. So that's a cartoon representation of exactly what I said. And exactly the same thing could be done by stereo as well. So you take an image, you note down all the image corners, and then you say that, okay, these are the image corners, and because these are the image corners, I, using a stereo camera, calculate what the XYZ are in the camera frame of reference, and then you say that my position as entity, so I know these things. Now the robot moves an unknown distance, let's say over here, and it can look at C2 and C3. So now my problem is using known C2 and C3 calculate position. And that's how I represent the problem. I moved an unknown world, so Q1 is unknown. But what I say is C2 was known. So I know this transformation, exactly where did I observe it? I know this transformation, exactly where did I observe it? C2 and C3, so C3. So I know C2, I know C3, I know these 2 transformations. So I calculate my position based on this thing, which is a localization problem. So I solve localization problem. Now what happens is that I observe C4, C5, C6, C7. Now I know my position, I know these transformations. So this position is the robot pose times this transformation, not going into mathematical detail, so I know this, and therefore I just populate this thing up in my map. Again, I travel an unknown distance over here, so I'll look at some new landmarks, let's say C8 and C9, and first using whatever I can see, C5, C4, C6, C7. So again, I travel an unknown distance. The first thing is I don't know my position. So I can look at C6, I can look at C5, I can look at C4. So using these transformations, using all these, I calculate my position, which is a localization problem, and then I register these up. So I forgot to mention over here, so this was the second part of the problem. So using position calculated from 1, calculate pose of the corners. And this is the mapping problem. So the overall thing is a little bit cluttered. So let me say that I traveled an unknown distance, 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 and there were some corners that I could look at. These are the new corners, and these are the corners which I re-saw. So that's how it goes. I first assume this to be identity. The robot always starts from its charger. Then I calculate all these positions, knowing my position. Then using this, I calculate my position over here. Then using this, I calculate all these positions. Then using 1, 2, these 3 positions, I calculate my position at this time. Then I calculate these positions. And you keep on doing is, this is slam. And this one specifically is known as a pose graph. It's not a linked list, it's a graph because eventually you can always come back to something again. So you come back to something again. So you take a circle. Now that was the first part that I wanted to speak about. So overall, we've seen, to summarize it up, the 2 hardest problems. Number 1 was localization. Where am I? It could have been solved at a global level pretty easily using my own variant of GPS, but then the motion models calculated errors by integrating signals, and the errors kept on increasing, and the observation models were problematic for the reasons that the observation signal could also have noise. So usually you fuse both of them up. You fuse a motion model and you fuse a observation model by the tracking applications. But then eventually what we observed, that the observation model, it turned out, had a bigger problem, and that was it assumed the positions of all landmarks was known. Because the position of the landmark was known, I could calculate my position knowing the landmark's position with respect to me as sensed by the LiDAR or the visual odometry camera. So then we said that, okay, first let's solve the problem of mapping, or how to calculate the positions of all these landmarks. And it was very simple. If I knew my own position, I know my position, I know the landmark's position with respect to me, and therefore I know the landmark's position. And we solve the 2 problems simultaneously, which is what we do first whenever any robot comes. We take the robot on a tour. So that's exactly what we did when you people joined the institution. We took you on a tour. So somebody guided you, you kept on looking at different buildings, somebody kept on telling you, this is CC1, this is the computer lab, this is the robotics lab, this is the library. And that's exactly what we do with the robot. We take the robot on the tour, and the robot keeps on looking here and there. It knows it started from the charger, so it keeps on calculating its position every time, and it keeps on looking at what are the different places of interest. And once it does that, it autonomously makes a map like this. This is if you were integrating LiDAR images, and if you were not integrating LiDAR images, you will get all the corners, and you can always connect them in order to make this same kind of a map. It could be 3D. So SLAM is the first thing to do, and what it does is that as long as my robot starts from the charger, it can always use its previous position to calculate its new position using localization and this known map. If the robot doesn't start from charger, it won't be able to solve the correspondence problem. It will look at the corner, but it will not know which corner is it looking at, so it will not be able to eventually solve that problem. And that constitutes the vision aspects of autonomous mobile robots. Okay, so These are practical examples of SLAM. The first one by a LiDAR, where you see this robot going and just projecting everything on the canvas and calculating its position based on how the different corners have moved. That's again the one that you see Microsoft Kinect, which has a depth camera and a RGB camera, wherein the robot is looking at different corners and projecting it up. And just for visual display, on the right is where you see the dense map, which is all the RGBD, which is all the points that it sees projected on an empty canvas. It's looking at how the different corners of different computer systems and bookshelves are moving. And of course, those are stationary, so it calculates its own position based on how these features appear to be moving in its own image. And that's the last one, which is our campus, and the black dots that you see in the screen are the different landmarks. So now you get realistic that the corners are of the buildings, of the trees, of the boundary, of the signboards, of the street lights that's visible in the image below. And the green one is the computed part, and the blue is what is the position of the robot at every point of time. That's what we calculated as Q0, Q1, Q2. So it's doing SLAM, it's calculating its own position based on the black dots or the landmarks. Now you also know practically how many landmarks are possible, and using that, it is correcting the black dots position or adding new black dots. That's how you see that as it goes along, the black dots keep on increasing. And this one is also what shows the pose graph, because it returned to the same position again, and you see loops based on which it is able to correct the positions. And finally, what you see is the map of the campus as made autonomously by the robot.